Hello students, in our last class I have discussed about the mu-J equation, and we have also observed that how can we find out the magnetic moment for lanthanide ions. Okay. In this class I will discuss about the few other things in the chapter of magnetochemistry. So let's start with the spectral properties. So for the low energy electronic transition, the Laporte orbital selection rule and the spin multiplicity selection rule should be obeyed. Okay. So when we talk about the electronic transition, we know that the electrons can jump from the ground state to upper energy state when we apply some amount of energy. It can be heating energy, it can be electrical energy, any type of energy. If I will apply some amount of energy, then the electron should be jumped from ground state to the upper energy state. But for this electronic transition, the two types of selection rule should be obeyed. The first one, that is known as the Laporte orbital selection rule, and the second one, that is the spin multiplicity selection rule. So first of all, we will discuss about the Laporte orbital selection rule. So any transition of electron within the same symmetrical orbitals is forbidden. That means the delta L is equal to 0 is forbidden and delta L is equal to plus minus 1 is allowed. What does it mean? We know that if the azimuthal quantum number, that is actually, if I say that the L is equal to 0, that means the S subcell. If I will talk about the L is equal to 1, that is our P subcell, L is equal to 2, that is our D subcell, L is equal to 3, that is our F subcell. So if delta L is equal to 0, then the energetically electronic transition, that is actually forbidden. That means the DD, FF transition, that type of transition should be forbidden. But if the azimuthal quantum number, that the change in azimuthal quantum number, that is plus minus 1, that means the D to F or F to D or F to G, okay, this type of electronic transition are allowed. Okay, so this is a very important rule. So according to the Laporte selection rule, that is the when the delta L is equal to 0, the electronic transition is forbidden. That means the DD or FF transition should be forbidden. But when the delta L is equal to plus minus 1, then the electronic transition is allowed. That means the D to F or F to D or F to G, this type of the transitions are allowed. But there are some limitations are also there. So if any centrosymmetric molecule be faced uneven environmental effect, then the inversion center of the molecule undergoes fluctuation from the original position. Then there appears the scope of orbital mixing, which rules out the existence of pure P or pure D or pure F orbitals. So the forbidden G to G or U to U transitions are relaxed. That means the delta L is equal to not equal to 0. So this type of things that is actually observed, that is known as the Fibronic coupling. So just I'm again explaining that this fact, that is, suppose I have a centrosymmetric molecule, means suppose I am talking about any type of the octahedral structure. Suppose MX6, N is the central metal and X is the 6 ligands surrounded by that central metal atom in case of octahedron geometry. So that is our centrosymmetry, means the molecule is totally symmetric. So obviously there should be a inversion center present in this molecule. But if I will say the other thing, if the ligands are not similar, suppose I am talking about ML4X2, this type of the complex, if the ML4X2, if it is trans, then there should be no mixing. But if I am talking about cis ML4X2 type of the molecule, then there should be a non-centrosymmetric nature. That means the inversion center is not there in case of the cis ML4X2 molecule, but in case of the trans ML4X2 molecule, there should be inversion center. That means that molecule is centrosymmetric. We know about the trans ML4X2. The central metal is there, the equatorial 4 bonds are there where the L should be there and the actual positions to X should be there. So that is a centrosymmetric molecule. Okay, inversion center goes through that central metal atom. That's why that is our centrosymmetric molecule, and that for trans ML4X2 there should be no mixing of orbital. But when we are talking about cis ML4X2, in that case we can observe the inversion center that actually vanishes, and in that case there appears a scope of orbital mixing which rules out the existence of the pure D type of the orbital. So for this case the delta L should not be equal to 0, and in that case the DD or FF transition may be allowed. Okay, so when we are talking about the centrosymmetric molecule, in the case of the centrosymmetric molecule, the delta L is equal to 0, that is forbidden, and delta L is equal to plus minus 1 is allowed. But when we are talking about the non-centrosymmetric molecule, in that case the delta L also not equal to 0, and obviously the delta L is equal to plus minus 1, that is also allowed. Okay, so in that case both things are allowed, that is delta L is equal to 0 or delta L is equal to plus minus 1. The both things are allowed when there is no inversion center. That means the molecule is not centrosymmetric one. Okay. Next, the second one, that is the selection rule, which actually based on the spin multiplicity. So the second one, that is the spin multiplicity selection rule. In that case, when the delta S is equal to 0, in that case that is our allowed transition. But when the delta S is not equal to 0, that is our forbidden transition. Okay, so when the delta S is equal to 0, that means that in case of the allowed transition, obviously the color intensity of the compound will be high. But when the delta S is not equal to 0, that is our forbidden transition, obviously the color intensity should be weak. So if electronic transition, when we are talking about the F to F electronic transition, that is forbidden when the complex ion have inversion center retained. Okay. So here I have drawn the CFT, means the crystal field splitting of the F subcell. So the three energy states should be there in case of the crystal field splitting of the F subcell. So these transitions should undergo to the UV region of the energy bands, but F to D transition is orbitally allowed and the absorption band will appear in the visible region, shows color. In addition, there is a possibility of electronic transition from L to N or M to L, that is ligand to metal or metal to ligand, that is also known as the charge transfer, that is LMCT or MLCT type of the complex. So the charge transfer bands are always more intense than the D to D or F to F transition. So the main thing is that when we are talking about the spin multiplicity selection rule, in that case when the delta S that is equal to 0, okay, that is our allowed transition, and when the delta S is not equal to 0, so that is our forbidden transition. So when delta S is equal to 0 means the spin of the both energy states are equal, then we can say that okay, then in that point the energy can, the electron can jump from lower to higher energy state. But when the spin of the two energy states are different, we can obviously say that there should be no electronic transition, or maybe transition is possible but the color intensity is very low because the possibility of the transition is very less in that case. Okay, so obviously in that case the transition should undergo to the UV region of the energy bands, But when we are talking about the F to D transition, that is the actually allowed, the Laporte allowed, and the absorption band will appear in the visible region, shows intense color. And in some cases we can also observe the ligand to metal charge transfer or metal to ligand charge transfer also. So in that cases, obviously the charge transfer bands are always more intense than the D to D or F to F transition. Okay, so here we have talked about the two type of transition. In case of the electronic transition, which is based on the Laporte selection rule and the spin selection rule. In case of the Laporte selection rule, we can say that when the delta L is equal to 0, that means the D to D or F to F transition, that is forbidden, but when delta L is equal to plus minus 1, that is allowed. And in case of the spin, when delta S is equal to 0, we can say that okay, this transition is possible, but when delta S is not equal to 0, this transition is forbidden. Another type of transition, that is ligand to metal or metal to ligand charge transfer, and this type of bands are very intense than the D to D or D to F or F to F, any type of the transition. So now again we are coming to the mu J equation. We know that the mu J, that is actually comes from the LS coupling, so we can write that mu L plus mu S vector, and that gives the G beta root of Jj plus 1. We have already talked about G. G is also known as the Zeroman ratio or the Landis G factor, or it can be also called the spectroscopic splitting factor. So in that case, we are talking about the case 1 and case 2. If the spin contribution, in the first case, if the spin contribution to mu effective is 0, that means mu S is 0, that means the S is 0. So obviously in that case the J is equal to L. So that is applicable for the diamagnetic complexes, and in that case the value of G, that is 1, that means the value of mu J, that is equal to mu of L, that is equal to beta root of L plus 1, L into L plus 1. In another case we can say if the orbital contribution to mu effective is 0, that means L is equal to 0. In that case the J is equal to S, so the G value, that is 2, and finally we come to the point that the mu J is equal to mu spin only value, which is obviously root over n into n plus 2 Bohr magneton. Okay. Next we are talking about the quenching of the magnetic moments. In some cases we can observe that the magnetic moment's value, it is just quenched. So why is this quenching is possible? So in presence of the crystal field, the orbital magnetic moment is somewhat quenched. Okay, when the crystal field splitting, we know about the crystal field splitting. So in presence of the crystal field, the orbital magnetic moment is somewhat quenched. We know that the T2G and the EG. T2G is known as the magnetic triplet and EG is known as the non-magnetic doublet energy states. So the orbitals in T2G the dxy, dyz and dzx are there. So these are the axial d orbitals. So these are of similar shape, and so the electron can move from one orbital to another easily. So if I will rotate that dxy to dyz to dzx by 90 degree, then we can come to dxy to dyz or dyz to dzx or dzx to dxy. So that means these orbitals are similar in shape. So the electron can move from one orbital to another, and the electron can rotate around them and generate orbital magnetic moment. So that's why we are saying that the T2G, that is the magnetic triplet. Okay, because in the T2G set of the orbitals are similar in shape, and the electron can move from one orbital to another easily, and the electron can rotate around them. So obviously they generate the orbital magnetic moment. But in case of the EG, we know that the EG, that is actually the axial the axial orbitals are there. So that is our dx square minus y square and dz square are there in case of the EG, and in case of the T2G, the non-axial d orbital, that is dxy and dyz and dzx are there. So in case of the EG, When we are talking about the EG, these are the axial orbitals, and we know about the shape of the z square and dx square minus y square. So these are not similar in shape, so the electron cannot move from one orbital to another, and for that reason we can't get any type of the orbital magnetic moment when the electron is situated in the EG set of the orbitals. So for orbital contribution to the magnetic moment, the following three conditions are to be satisfied. So we are talking about the quenching of the magnetic moment. So if the orbital contribution is there in the molecule, so then the magnetic moment can be quenched, and it follows the three conditions. The first condition is that the orbitals should be degenerate. What is that point? The orbitals should be degenerate. Second is the orbitals should have similar shape and size. And number three is that the orbital should not contain electron with identical spins. So in magnetic moment, if the orbital contribution is present, that means the orbitals should be degenerate, orbitals should have the similar shape and size, and orbital should not contain electron with the identical spins. So these three conditions are very, very important for the orbital contribution to the magnetic moment. And in that case, we can easily say that the T2G set of orbitals, these are degenerating. Degenerate means the similar in energy, and the T2G set of orbitals, which are actually the non-axial d orbitals that have the similar shape and size, and the orbital should not contain electron with identical spin. Okay. So next we are coming to the thumb rule. What is that thumb rule? Thumb rule says that when the ground state of a complex is either A or E, okay. Again, I am repeating, when the ground state of a complex is either A or E, the orbital contribution will be quenched. That is, there is no orbital angular momentum for these states. Okay, so important that when the ground state of complex is either A or E, the orbital contribution will be quenched and there is no orbital angular momentum for these states. What is the reason? The reason is that A state is non-degenerate because it has only one level. Okay, we are writing that A for only one energy level. Hence, the rotation cannot change one orbital into another equivalent orbital because only one degenerate means the one energy level is there, so there is no other orbital, the single orbital is there, so the electron cannot move from one to another orbital, another equivalent orbital, and for that reason the A state is non-degenerate, and in that case we can observe no orbital angular momentum. And the E state that is doubly degenerate, which means that there are two energy levels with same energy. One orbital cannot be changed into another by rotation because their shapes are different. When we are talking about E, means when we are talking the T2G or EG, in case of the EG, we know that the axial d orbitals are there, that is dx square minus y square and dz square. So in that case, we can't change the electron's movement from one orbital to another because the orbitals are not similar in shape and size, because dx square minus y square and dz square, these two orbitals are not similar in shape and size. So for that reason, the E state, which contains the two energy levels with same energy, but one orbital cannot be changed into another by rotation because their shapes are different. But when we are talking about the T state means we know that the T2G set. So the T state is triply degenerate state caused by the T2G orbitals, that is dxy, dyz and dzx, and these are the non-axial d orbitals and their similar shape and size. Thus, if an electron is present in dxy orbital, it can move to dyz, it can move to dzx by simple rotation by 90 degree, and electron can rotate in an orbit producing the magnetic moment. So when the ground state is A or E, So there should not be any type of the orbital magnetic moment, but when the electron is situated in the t state, then the electron can rotate from one orbital to another orbital, which produces the magnetic moment. So here I am just written a table, that is I have written the octahedron complexes. For octahedron complexes, the D1 to D10 electronic configuration. So when the octahedron D1 complex is there, the ground state term, that is 2T2G. Okay, the ground state term is 2T2G. So the ground state term, if the T is there, so obviously the orbital contribution is there. When the electronic configuration is D2, in case of the octahedral complex, the ground state term is also T1G, the triplet T1G. So the orbital contribution should be there. When we are talking about the D3, the ground state term is 4A2G. So the ground state term is A or E. We have already told in the thumb rule that if the ground state term is A or E, so there should be no orbital contribution. So in case of the D3 octahedral complex, the ground state term is A to G, so that's why there is no orbital contribution. The similar thing is also applicable when we are talking about the before octahedron complex in high spin state. The ground state term is 5 EG, means the pentect EG. So E is there, that means there is no orbital contribution. But when we are talking about the before octahedron complex in low spin complex, the ground state term is triplet T1G, so the T is there, so the orbital contribution should be there. In this way, I have written all the electronic configuration for the octahedron complexes like D5, D6, D7, high spin and low spin cases, and where the ground state term is T, there should be orbital contribution, but where the ground state term is A or E, there should not be any type of the orbital contribution. Okay, and in case of the D8 and D9 also, we can also check that in case of the D8 octahedral complex, the ground state term is A2G, so there is no orbital contribution, and in case of the D9, the D9 octahedral complex, the ground state term is 2EG, means E is there, so there is no orbital contribution. So that is a very important part, that the magnetic moment, the value of the magnetic moment can be quenched. If the orbital contribution is there, so obviously the magnetic moment value should be quenched. And how can we determine that is there any orbital contribution in the magnetic moment? Simply we have to find out what is the ground state terms. If I know the ground state term, means if it is A or E, so there should be no orbital contribution. If in the ground state term the T is there, the T, the triplet, that is dxy, dyz, dzx, the non-axial d orbitals are there, so the electron can move one orbital to another easily, and for this reason the orbital contribution should be present there, and the value of magnetic moment when the ground state term is T, it should be quenched. Next, in case of the tetrahedron complexes, actually mainly we have talked about the octahedron complexes, but we have to also say about the tetrahedron complexes, the orbital contribution is also present. For example, nickel 2 complex, that is actually our D8 system, that is our E4T24. We know about that in case of the tetrahedron, we can't use the G, that is the Girardet part, means not EG or T2G, we have to write E or T2. So if I write the Ni2 complex, Ni2 tetrahedron complex, the electronic configuration is D8, and that is actually E4T24. And in that case, the ground state term is T1F. Okay, means the T1, T is there. So in case of the nickel to tetrahedron complex, the ground state term is T. So obviously the orbital contribution should be there. Few exceptions are also there. Just I have written here the exception, that is if I have NiNH3 whole 6 2 plus, that is nickel hexamine 2 plus complex, the electronic configuration, that is D8 octahedron high spin complex, and the ground state term is A2G. Okay, so in case of this type of the complex, the NiNH3 whole 6 2 plus, that is our D8 octahedron high spin complex, so the ground state term is A to Z. Okay, so in that case obviously the orbital contribution should not be there. Okay, so in this way we can calculate the magnetic moment by using the simple Mu's equation for the lengthened elements and the spin only magnetic moment, that is the mu s. If I will asking about the mu s, we can easily calculate the magnetic moment for the transition elements. And then we have also discussed about the two type of the selection rule, which is important for the electronic transition, that is Laporte selection rule and the spin selection rule. And by using these two rules we can say that the D to D or D to F, this type of the transitions are not possible, and if the spins are not equal of the two energy states, then we can also say that the electronic transition is not possible. Then we have also discussed about the orbital contribution to the magnetic moment. For this we have used a simple thumb rule. In that thumb rule we had seen that if the ground state term, that is T, that is triplet, in that case the orbital contribution should be there, and if the ground state term is A or E, in case of the octahedron or tetradium complex, whatever may be, then in that case the orbital contribution should not be there, because the electron cannot move from one orbital to another orbital in case of the A or E ground state term symbols. Okay, so this is all about our PG semester 1 inorganic unit 2 magnetochemistry portion. This is also applicable for the BSc third year students also. Okay, thank you.